Learn maths from home with me, myself Nitin Mittal. Today I am going to explain you exercise 1.4 chapter 1 real numbers of class 10. So let us start. Hello friends. Today we are going to discuss exercise 1.4 of chapter 1 real numbers. But before we start exercise 1.4, there are three important theorems given in NCERT book that we must do. The first theorem is theorem 1.5 given at page 16 of NCERT book 10th class. Theorem states, let x be a rational number whose decimal expansion terminates, then x can be expressed in the form of p over q, where p and q are coprime and the prime factorization of q is of the form 2 raised to power n into 5 raised to power m, where n and m are non-negative integers. Now, in this theorem, what is being actually stated that if you consider any decimal number that is terminating, for example 0.25, 0.5, any number whose decimal expansion terminates, if you convert that in p over q form, and after converting into p over q form, if you will see the prime factorization of q, you will find that the prime factors of q will be either 2's or 5's or 2's and 5's only. It won't have any other prime number other than 2 and 5. Right? So let me take one example. So let us take an example. I am taking a decimal number, any number randomly, 0.375. Now it terminates. Now if we convert it into p over q form, how we will convert? 3 plus decimals means 1000. Right dear? Now we have to convert the numerator and denominator in coprime. So we will do cutting as much as possible. So we can cut on the table. We can cut on 25. It's up to you. You can cut on 5 or 5 and again like that. So let me cut it. 25 40 is 100. 25 4 is 100. So 25 12 is 300 and 15 is 375. And further if we see, yes, it is still, we can do cutting. It is 3 by 8. Right? Now we have converted the decimal number into p over q form, that is 3 by 8. Now let me see, here q is 8, so prime factors of 8 are 2 into 2 into 2. So if we want to write as 2 raised to power n into 5 raised to power n, can I write it as 2 raised to power 3 into 5 raised to power 0? See, because they said that n and m are non-negative integers. So these are non-negative integers. Right? If we leave the negative integers, so we will be left with non-negative integers. You can say non-negative integers are whole numbers. Right? So in this example we have seen a decimal number whose that terminates, decimal expansion terminates. If we convert into p over q form, then the prime factors of q must be of the form 2 raised to power n into 5 raised to power m as shown here. where n and m are non-negative integers. So this is what theorem 1.5 states. Okay, if somebody asks you by giving you a decimal number and ask whether it has in p over q form, the prime factorization of q will be of what type. So you can simply see if decimal number terminates, then the prime factors of q must be of the form 2 raised to power n into 5 raised to power m, and if it is non-terminating repeating, it means it must not be of the form 2 raised to power n into 5 raised to power m. Right, this is theorem 1.5. Now let we move to next theorem. So the next theorem is converse of theorem 1.5. It states, let x is equal to p over q be a rational number. Now we are not having decimal number, we have number in the form p over q. So they say if let x equal to p over q be a rational number such that prime factorization of q is of the form 2 raised to power n into 5 raised to power m. So if we have a number in form p over q, and if we check the prime factorization of q and it comes to be 2 raised to power n into 5 raised to power m, then we can declare that x has decimal expansion which terminates. So we need not to convert into decimal, we can simply see the prime factors of q, and if the prime factors of q is of the form 2 raised to power n into 5 raised to power m, then we can simply state that the decimal expansion of the number must terminates. So for that we need not to do in the division, we need not to convert the number p over q form into decimal. Without converting, just by seeing the prime factors of q, we can decide that decimal expansion will terminate, right? And if the prime factorization of q is not in the form 2 raised to power n into 5 raised to power m, then it will be non-terminating repeating, which is being stated in theorem 1.7. So let we read that also. Let x is equal to p over q be a rational number such that the prime factorization of q is not of the form 2 raised to power n into 5 raised to power m, where n m are non-negative integers. Then x has a decimal expansion which is non-terminating repeating, right? So if the if the prime factorization of q is of the form 2 raised to power n into 5 raised to power m, then the decimal expansion will be terminating. And if the prime factorization of q is not of the form 2 raised to power n into 5 raised to power m, we can state that decimal expansion will be non-terminating repeating. Repeating can also be called as recurring, right? So this is theorem 1.7. So what we conclude? We conclude rational numbers can be represented in two ways. One in the form p over q, where p and q are integers and q not equal to 0. You have done in class 7. And one, rational numbers can also be represented in decimal form. But in decimal form, rational numbers will be of two types. One terminating, one non-terminating repeating. So let we see some of the examples. Here we go. So the examples, if you see 1 by 2, denominator is 2, right? And if we convert into decimal, it is 0.5. 1 by 4, what is the q? 4. 4 prime factorization is 2 into 2. So it is of the form 2 raised to power n into 5 raised to power m. Here 5 raised to power m is 0 here. 5 raised to power 0 is 1. So 0.25. 1 by 8, 8 again 2 into 2 into 2, no 5 is there. So in prime factorization of q, it must be all 2's or all 5's or the combination of 2's and 5's. Then we can state that the decimal expansion will terminate. So here we have done the decimal expansion for checking purpose whether it really terminates or no. Otherwise you need not to do decimal expansion. Without doing decimal expansion, you can simply see the denominator prime factorization, and if the prime factorization of denominator is in the form 2 raised to power n into 5 raised to power m, you can state the decimal expansion will terminates, right? And whereas the numbers in the form p over q, where the q is prime factorization of q is not in the form 2 raised to power n into 5 raised to power m. Here you see 15. Prime factorization is 3 into 5. 5 is there, but 3 is also there. So 3 is there. So it is not of the form 2 raised to power n into 5 raised to power m, as 3 is there. So you see its decimal expansion is non-terminating repeating, right? Let us start exercise 1.4. The first question, without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or non-terminating repeating decimal expansion. Question number 1. So in this they have given many parts of the question. 10 parts are being given in NCERT book, but the steps we must understand before we start the question. The first important step which many students used to ignore is the number which is given in the form p over q, you have to ensure that the numerator and denominator of the given number must be co-prime integers before you make any decision regarding terminating decimal expansion or non-terminating repeating decimal expansion. Let me clear it with one example that many students used to do. Suppose the question is 21 by 15. Now what students used to do? They just see 15 and they think for the prime factorization of 15, that is 3 into 5, and they just conclude that as 3 appears in the prime factorization of q, it means it is not of the form 2 raised to power n into 5 raised to power m. Therefore, the decimal expansion of the given rational number will be non-terminating repeating. But students, it is wrong. It will be wrong, your answer. So what is the correct way? The correct way, as I mentioned, first you have to ensure whether numerator and denominator are co-prime or no, and if no, you have to convert them, you have to make them co-prime by cutting them on common factor table. So 21 and 15 both are divisible by 3, so we'll cut 21 and 15 by table 3, we will get 7 over 5. Now further cutting is not possible, and we see the prime factorization of q is of the form 2 raised to power n into 5 raised to power m. So we can conclude the decimal expansion of the given number will terminate, and this is the correct way of writing the solution. In this we have used the theorem 1.6 given in NCERT book. So this is the way how we have to do this question. One more question, exercise 1.4, first question, third part, I have taken from book. Now 64 over 455. So what we have to see whether its decimal expansion terminates or it will be non-terminating repeating. So first thing we have to ensure that there should be nothing common between numerator and denominator, and other than 1 means they must be co-prime. So here we see 64, right? It is 2 raised to power 6. 455, of course it is odd number, and this one is even number. 64 is divisible only by 2, smallest prime factor, right? Now it means these numbers are already co-prime, right? So what is the next step? We will see the prime factorization of 455. Let me see. 455 divisible by 5 clearly. 9 5s are 45, right? 5 1s are 5. On the table 7, 7 1s are 7, 13 7s are 91, we all know. So 455 is equal to 5 into 7 into 13. So here prime factorization of denominator of the given number is not of the form 2 raised to power n into 5 raised to power m. So decimal expansion of this number will be non-terminating repeating. So here we have used theorem 1.7. So this is how we have to do this question. Now next question, question number 2. In question number 2 they are saying whichever first question parts are having terminating decimal expansion, convert them in decimal form. So how to convert them in decimal form? For this I am taking first question, first part, that is 13 over 3125. So let me see the prime factorization of denominator 3125. If we see, divisible by 5, so 6 5 is 30, 2 is 10, 5 is 25, again on 5 125, 5 25, one more 5, so it is 5 times 5, so it is 13 over 5 raised to power 5. So clearly here we can write the same way. Here prime factorization of denominator is of the form 2 raised to power n into 5 raised to power m. As 2 is not there in the denominator prime factorization, it means it must be 2 raised to power 0. We need not to show, and if you show, there is no harm. You can write here 13 over 2 raised to power 0 into 5 raised to power 5, right? Because anything raised to power 0, 1. So prime factorization of denominator is of the form 2 raised to power n into 5 raised to power m, and m are whole numbers. You can write whole numbers, no negative integers or whole numbers, right? So decimal expansion of given number is terminating. So this is the solution of first question, but we have to do second question, that is we have to convert this terminating number. We know it will terminate, but we have to see the decimal form. So how to proceed? 13 over 3125 we will write as 13 over 5 raised to power 5. You need not to divide 13 by 3125. You need not to do actual division. Without doing actual division, we can convert easily into decimal form. The method is, you have to ensure in the denominator prime factorization, you should have equal number of 2's and 5's. Now if you see in denominator we have 5 5's, 5 times 5, so same number of times we must have 2's also. So we will use the concept of equivalent fraction, equivalent rational number, so we will multiply by 2 raised to power 5 over 2 raised to power 5. Now you see in denominator we have equal number of 2's and 5's, right? So it will become 10 raised to power 5, and numerator will be 13 into 32. 13 2s are 26, 2, 13 3s are 39, 39 into 41 over 10 raised to power 5 means 50 means 5 place decimal, so it will be 0.00416. So this is how we have converted into decimal without any actual division. Let me see one more example. Let me take one example from my own. Let me take number 11 over 2 raised to power 3 into 5 raised to power 2. Now what I told you, to convert it into decimal, you should have equal number of 2's and 5's in denominator. So if we see there are 3 2's and only 2 5's are there. So which one is less? 1 5 is less. So we'll multiply both numerator and denominator by 1 5. So numerator will become 55 and denominator will become 10 raised to the power 3. So it is 0.055. So this is how we have converted into decimal. So this is your second question of exercise 1.4. First part. In third question first part they are saying the following real numbers have decimal expansion as given below. We have to decide whether they are rational or no, and if they are rational and of the form P over Q, what you can say about the prime factors of Q. Now friends, we have already done the numbers whose decimal expansion terminates or non-terminating repeating, those numbers are rational numbers, and the numbers whose decimal expansion is non-terminating and non-repeating, those are irrational number. And if you see the first part, its decimal expansion terminates, there is no dots after this or bar is there, so it means it terminates, so we can conclude that it is rational. The first answer of the question is it is a rational number as decimal expansion terminates. Now this is one answer, but they are asking two things. Okay, if it is a rational number, what you can say about the prime factorization of denominator Q. So we know rational numbers can be expressed in P over Q form. So we will write in P over Q form. We are going to use theorem 1.5 here, right? In P over Q form, prime factorization of this number must be, in P over Q form, prime factorization of Q of this number must be of the form 2 raised to power n into 5 raised to power m NMR whole numbers. You can write non-negative integers. So this will be the answer, that the prime factorization of Q of this number must be of the form 2 raised to power n into 5 raised to power m. This is the first part. Second part, it is 0.120120012000 12000 dots. Now in this number, if you see, it is first of all non-terminating. You can see the dots represents it is non-terminating, right? It doesn't terminate. So now we have to see whether it repeats or no. So let me see, here it is 120, it is 1200, 12,000. So what we see, it is non-terminating, non-repeating. And in case the decimal expansion is non-terminating and non-repeating, it is an irrational number, right? So we'll write as decimal expansion is non-terminating and non-repeating, so it is an irrational number. And as it is irrational number, so our answers completes here. We need not to do anything further. Third part, it is 43.123456789 bar. Bar is the clear indication of repeating, right? So it is non-terminating, repeating. So what we will write as decimal expansion is non-terminating, repeating. So it is a rational number. So this is one part of the answer. As it is a rational number, now we have to talk about the prime factorization of q. We'll write in p over q form, prime factorization of q must not be of the form, we are using theorem 1.7, 2 raised to power n into 5 raised to power m. N and m are non-negative integers, you can say whole numbers. So here is the solution of this part. So guys, I hope you understood. Thank you. See you with the next video, in which we will be doing chapter 3, right?